Welcome friends to the third lecture of green chemistry. In today's lecture we will be discussing about green catalysts. In last two lectures we have seen about the principles of green chemistry given by Professor Anastas, and in the last lecture we had seen about various types of green reagents and how those can be used in order to replace our normal reagents, or how we can use the normal reagents supported by polymer so that the reactions could be carried out in a environmentally benign methods. So now today we will be looking after green catalysts. We know that the catalyst plays an important role in carrying out organic reactions, or in carrying out any reactions. Catalyst plays an important role. In the last lecture we had seen that a reactant is when mixed with a reagent, it gives us a product. So this is our basic reaction condition that is normally carried out. A reactant is when treated with a reagent, it will be converted into a product. But many times it happens that this conversion rate is very slow. So we need to speed up the process so that we get the product in a large amount and quickly also. So to do that, we need to add a certain amount of small other substance that we call it as a catalyst, which generally does not take part directly, but indirectly it takes part in the reaction so that the reaction gets speeded up. The equilibrium in the reaction is reached faster, and the properties of this catalyst we have studied in our undergraduate levels. So we will not elaborate the properties of catalysts here, but the catalyst plays an important role in carrying out the reactions. Catalyst plays a major role in establishing the economic strength of the chemical industry, and the clean technology revolution in the industry provides new opportunities for catalysis and catalytic processes. So when we are moving ahead in the economy, which is driven by our chemical reactions, chemical industries, there the catalyst plays an important role in carrying out the reactions. In green catalyst, we will be looking after different types of catalysts. One of them will be the acid catalysts. Then we will also see about the oxidation catalysts. We will see about the basic catalysts. Then we will see phase transfer catalysts. This is important for carrying out organic reactions as well as for the exams also. The phase transfer catalyst. Then we will see about the biocatalysts. So we will see these many different types of catalysts. In today's lecture, we will be concentrating more on acid catalyst, oxidation catalyst, and basic catalyst. In the next lectures, we will look after the phase catalyst as well as phase transfer catalyst as well as the biocatalyst. As these are a little bit longer topics, so we will take them separately. In today's lecture, we will be concentrating more on the acid catalyst, oxidation catalyst, as well as the basic catalysts. So first let us see about the acid catalysts. There are many different types of acid catalysts that are being used. The traditional acid catalyst has a difficulty or a problem of corrosion. They are highly corrosive. So the problem of corrosion arises in the normal acid catalyst. Uh, in order to get rid of this corrosive properties, as well as the acid catalyst being hazardous and toxic. So in order to get rid of this, we can use other methods with same catalyst. We can use in a different ways so that they becomes greener. Like for example, we can have hydrogen fluoride. Hydrogen fluoride is one of the acid catalysts which is majorly used in many different industries, like we are using it in petroleum industry as well as in production of linear alkyl benzenes. This catalyst has been used, but it has a corrosive property, it is hazardous as well as it is toxic. So in order to overcome these problems, we can use it successfully by replacing this HF or a hydrogen fluoride by a fluoridide silica gel, silica alumina, by a fluoridide silica alumina catalyst. This is prepared by treating the silica alumina with either NaF, that is silica alumina is treated with either sodium fluoride or with a calcium fluoride, and the product that we get it will be activated, and so the silica alumina fluoride is generated. This silica alumina fluoride does not require special material for construction, as well as it involves with lower operating costs and eliminates the need of waste disposals. So this gives us an advantage over the other materials. Similarly, we can use other reagents, other acid catalysts like one Lewis acids. Lewis acids are known to carrying out many different types of reactions like FC acylation reaction, Michael addition reactions, or Mannich reaction, as well as the other reactions are being carried out by Lewis acids. These Lewis acids, one of the Lewis acids being used is scandium triflate. The scandium triflate is nothing but scandium trifluoromethane sulfonate. That is, we have a trifluoromethane attached to sulfate, so that we will get a scandium triplet. This is one of the very good Lewis acids being used in many different types of reactions. This can be used as a true catalyst where it is required in a very small quantities and rather than in stoichiometric amounts with the other catalysts. So this has its own advantages, and it can be used in different reactions, but this has a problem that it is corrosive, like what we have it for HF. This is also, Lewis acids are also corrosive catalysts. So in order to overcome this corrosiveness of the Lewis acids, what we can do is we can encapsulate this scandium triflate into micro encapsulated, we can use it, so that we will have a micro encapsulated scandium triflate. So micro encapsulated scandium triplet can be used to carry out different types of reactions over here. Like for example, we can use this for carrying out FC acylation reaction with acetic anhydride. So we can carry out this micro encapsulated scandium triplet can be used for simple Friedel-Crafts acylation reaction. Similarly, we can use this for carrying out Michael addition reactions like this. We can have it micro encapsulated scandium triflate in acetonitrile at room temperature. In 6 hours we can get the product. So this product we can get it very easily from this particular reaction. Similarly, we can use it this catalyst for carrying out reactions like Mannich reaction, like benzaldehyde when mixed with say aniline and in presence of micro encapsulated scandium triplet. Most of the reactions here with scandium triplet are either at room temperatures or slightly temperatures. So these are also taking care of the principle of green chemistry that we need to use lower energy requirements for the reaction. So this color codings we are using it, which will be indicating that which part of this is coming from which of the reactants. This blue part is coming from benzaldehyde, pH, that is phenyl ring and a carbon. This phenyl ring and a nitrogen are contributed by aniline, and the other parts are coming from this alkene or enol silicate. Silinol. We will get this particular product. Mannich reaction we can get it. Similarly, we can use it for Mukayama aldol condensation also. Similar reactions we can have it, like when benzaldehyde reacts with silylenol ether, benzaldehyde reacts with silylenol ether in presence of microencapsulated scandium triplet. In dichloromethane, normal reaction takes place at minus 78 degrees Celsius. If microencapsulation is taking place, then it can be it is reported in at room temperature also. So we will have the product as benzaldehyde methyl group with OH attached to cyclohexane ring with a carbonyl group attached. So this will be our Mukayama aldol addition reaction. So such reactions can be easily carried out by using acid catalysts like Lewis acids. Similarly, we have seen the fluoride reactions we have used it, and also this Lewis acids. Similar to this, we can also use zeolites. We can use zeolites for different reactions. Zeolites are very important in petroleum industries. They are widely used in petroleum industries for either cracking or hydrocracking. Cracking is generally used for manufacturing petrol, and hydrocracking is used for manufacturing diesel as well as jet fuels. In hydrocracking, it is present in presence of hydrogen, and without presence of hydrogen, it will be called as a cracking process. But these zeolites can also be used as an acid catalyst in many different reactions for synthesis of fine chemicals as well as specialty chemicals. We can use this zeolites. So it has a great importance in organic chemistry. We can react with the alkene with ammonia in presence of silicate like pentasyl zeolite at 300 degrees Celsius and 300 atmospheric pressure. We will get tertiary butyl amine as a product. So tertiary butyl amines can be easily obtained. Similarly, we can use it for ring opening reaction, epoxide opening reactions. Same pentasyl zeolite can be used in either liquid or gaseous state. The reactants can be taken in liquid or gaseous states, and the product contains CH2CHO. So an aldehyde can be generated from this epoxides. So this is how we can use this zeolites. Zeolites are nothing but microporous aluminosilicate minerals. These are microporous aluminosilicate aluminosilicates, which are commercially used as either adsorbents, excellent adsorbents, or as a acid catalysts. So they can be used either as an acid catalyst or as an adsorbents. They are generally used in petroleum industry for either cracking or hydrocracking processes. In different other reactions also we can use this aluminosilicates. Similarly, we can use other reagents like Clasic. As a acid catalyst, we can use Clasic. Clasic is nothing but it is a zinc chloride supported on montmorillonite K10. Supported on montmorillonite K10. So this will be giving us different other types of reactions, which are special reactions, and sometimes highly unknown reactions also can be carried out by using Clasic. Clasic has been used to catalyze generally Friedel-Crafts reactions, various different types of Friedel-Crafts reactions, and also in preparation of benzothiophene from the cyclization of phenyl thioacetals. So we can use this Clasic for synthesis of benzothiophene from phenyl thioacetals. If we react it with Clasic, that is zinc chloride supported on a montmorillonite K10, then in presence of chlorobenzene at 132 degrees Celsius, this will generate benzothiophene. So benzothiophene can be easily obtained from this. Similarly, the alkylation or olefination of benzaldehyde. Similarly, olefination of benzaldehyde can be carried out by using this Clasic by a mechanism which was previously unknown. Like for example, we can have benzaldehyde can be reacted with say tetramethyl ethene in presence of Classic EPZ10 at room temperature, it gives us the alkene product. This product was previously unknown, or the mechanism is also completely unknown. We get different types of reactions. Some highly important products can be obtained. Commercial products can be obtained by using this green catalysts. So this is one of examples for acid catalyst. Similarly, we can use it for basic catalyst and oxidation catalyst also. Let us see it first for oxidation catalysts. Oxidation catalysts like molecular sieves can be used as an oxidation catalyst. Molecular sieves are the materials which are having small pores and uniformly sized pores. So these are very important that they have uniformly sized small pores are present in it, so that they can absorb small molecules in its pores. So adsorption of small molecules can be easily done, and large molecules can be taken care of. They can be moved away. So this molecular sieves can be used for filtration processes also. For large filtration processes, we are using these molecular sieves, as they are having small pores, so they can easily absorb the small molecules, and they are having uniformly sized small pores, so small molecules can be easily absorbed, so they can be easily separated from large molecules. So this is one of the uses for molecular sieves, but it can also be used for carrying out reactions. Selectively, we can use this for carrying out certain reactions to give us a particular products as a major product in the other different reactions. So these pores are of diameters which are enough to accommodate small molecules, while large molecules cannot be absorbed. They are used for the purification processes, as well as for petroleum industries, and for different other reactions like carrying out the oxidation reactions, for partial oxidations of substrates. Like for example, we can have molecular sieves based on titanium, that is titanium silicates like TS1, and vanadium silicates. We can use titanium silicates or vanadium silicates. Titanium silicates are used for oxidation or hydroxylation of phenols. Phenols can be hydroxylated in presence of titanium silicate TS1 and hydrogen peroxide to give us hydroquinone as the major product, in 81% yield, and we can get also resorcinol in 7% yield, and we can get catechol in 12% yield. So we can get hydroquinone as a major product. Along with that, resorcinol and catechol can be obtained when we are doing hydroxylation of phenols. Similarly, vanadium silicate molecular sieves are capable of selectively oxidizing 4-chlorotoluene to 4-chlorobenzaldehyde. So we can do the reaction oxidation of 4-chlorotoluene, that is methyl group can be oxidized to aldehyde selectively without further oxidizing it to acids. We will obtain the product as benzaldehyde Parachlorobenzaldehyde as 66% yields, plus we also have benzyl alcohol, parachlorobenzyl alcohol as 21%, and 3-hydroxy 4-chlorotoluene as 8% product. So we can have this different products. We can obtain it from vanadium silicates as well as titanium silicates. So oxidations can be carried out uh, with using H2O2 by using catalysts like titanium silicates or vanadium silicates, which are molecular sieves. So they can be easily used for as an oxidation catalyst. Similarly, we can use basic catalysts. Basic catalyst reactions are very few reactions are being reported, but they can use basic catalysts like magnesium oxide or potassium hydroxide. We can use it, or NaOH can be used. These NaOH, magnesium oxide or potassium hydroxide can be supported over the polymers, and then they can be used it. So they can be supported over alumina or other solid surfaces, and then they can be selectively used to carry out reactions. Like for example, magnesium oxide can be used for alkylation of phenols. Phenol can be alkylated in presence of magnesium oxide to give us 2,6-dimethyl phenol. Similarly, we can use side chain alkylation reactions in presence of potassium hydroxide supported over alumina to give us a side chain alkylated product. Similarly, we can use isomerization reaction NaOH supported over alumina to give us the isomerized products where the double bond is shifting as an exocyclic double bond, or the second product can be obtained by when this double bond is shifted over here, this bond breaks and moves over here, and this bond is then getting attached to this carbocation being generated over here, so that we will have a 1 2 3 4 5 and 6 membered ring, and this will be the 5 membered ring. So this 5 membered ring and the outside 6 membered ring, we can obtain it. So we can have the two rings being generated over here. So this isomerization reactions can be carried out by using basic catalysts. So this was for the catalysts. We can use this green catalyst for many different types of reactions. So we have seen it about the acid catalyst, we have seen about the oxidation catalyst, and then we have also seen about the basic catalyst. The examples for basic catalysts are very few, but generally acid catalysts are used in very many different types of industries. For particularly for petroleum industries, we are using acid catalysts. Similarly, oxidation catalysts are also used for generating specialty chemicals or special chemicals. We can use it for that. So thank you very much for this lecture.